Welcome to this presentation about biomedical engineering. My name is Tríona Lally. I'm a professor in biomedical engineering at Trinity College, Dublin, and I teach on this course in biomedical engineering. Today, I'd like to give you an overview of this course to help you better understand what biomedical engineering is, what jobs a biomedical engineer might do, and a little bit more about the programme itself at Trinity College. So before I talk about biomedical engineering, it's worth understanding what all engineers have in common and some of the attributes that are typical of an engineer. Engineers are typically problem solvers. They like putting ideas into practice and looking at providing solutions to unmet needs. Generally, engineers have an aptitude for science and mathematics, and they think logically and creatively to find solutions to problems in everyday life. In biomedical engineering, these problems tend to be those related to healthcare and the body. Because engineers often are from diverse fields, have to work together to solve these problems, it's important that engineers can communicate effectively and work in teams together. As you may be aware, engineering is broad in that you can be an engineer in many areas, applying your engineering knowledge to a number of applications. This can range from designing bridges, such as in cases being a civil engineer, to aeronautics, where you're looking at the design of planes, for example, or mechanical engineers, where you're more interested in designing cars and engines. In biomedical engineering, we're looking at problems in medicine or healthcare. In general, biomedical engineering is considered the application of principles of engineering to the advancement of healthcare and medicine. It is at that interface between engineering and medicine, where you use a lot of the skills that are typical of engineers, such as physics, chemistry, mathematics, computing, and so on, to solve problems that occur in the body. As a result, you also need to have knowledge in the medical areas or the biosciences, such as biology and molecular science. Biomedical engineers generally design and develop medical devices and implants. They also can design diagnostic equipment, and they're involved in developing materials also that go inside the body. So even though biomedical engineering is a subset or specialization in engineering, it too is quite broad, and there are many applications in this area. So let's look at some examples of biomedical products, because it helps to understand what it is you learn in the biomedical engineering program to be in a position to design and develop these particular medical devices or techniques in the biomedical engineering sector. So you may be familiar with artificial hips and knees, for example, or prosthetic devices. These are designed by biomedical engineers who use their knowledge of both the anatomy of the body and materials and load bearing to design devices that can replace these failing organs in the body. Other devices designed by biomedical engineers include devices such as these shown here, cardiovascular stents. These metal mesh structures are designed such that they can be opened up inside arteries in the body that have become blocked due to disease. These devices have struts, as you can see here, smaller than a human hair, and yet they have the strength to open up and restore flowing blood in a vessel that has become blocked due to the progression of atherosclerotic or cardiovascular disease. Another area where biomedical engineers develop products is in the area of surgical instruments, where through procedures like keyhole surgery, small devices can be placed inside the body to carry out a surgical procedure. Biomedical engineers are also involved in life support systems like ventilators, which we hear a lot about at the moment. They're also involved in the growing and exciting area of tissue engineering. Tissue engineering is the development of tissues in the body, often actually developed in a lab, that can replace the tissues in the body. This is using knowledge of forces and the knowledge of biology and how cells respond to stimuli or forces to generate tissues that are similar to those in the body. So we can replace damaged tissues when there is no alternative, such as no transplant tissues available. Another area where biomedical engineers are involved is in the area of robotics. Here we can see a Da Vinci system, which can actually carry out a surgical procedure in a remote fashion, whereby the surgeon might not even need to be in the same country as the surgical procedure is being carried out. Other areas you may be familiar with, prosthetic limbs, as shown here, which we've seen in athletes in recent years. These too are designed by biomedical engineers, along with the very strong and advancing area of medical imaging. Medical imaging is designed by engineers such as CT imaging or magnetic resonance imaging to aid in the development and treatment of individuals with disease. It would be very difficult, for example, for a neurologist to diagnose a disease without the advances that have been made in medical imaging by bioengineers. So at this stage, you will see that biomedical engineering is not a subset of modern medicine, but rather modern medicine is to a large extent the product of the technology and the tools that have been developed by biomedical engineers. So here's another example which will aid in you understanding the role of a biomedical engineer in improving the quality of people's lives and the interface with medicine. So I have shown you a stent, but perhaps it's worth looking at this a little bit more closely to see how engineers are involved in this whole procedure and the development of these products, but also even in the diagnosis of the disease that it treats. So here you can see medical imaging being used to identify a blockage in an artery on the surface of the heart. This blockage, if not treated, will result in a heart attack for this individual. And so at this point, a device must be deployed or a surgical procedure carried out in order to restore blood flow. Traditionally, open heart surgery would be conducted in order to bypass this vessel with another conduit, another tube, to ensure that blood could flow again. But in recent years, these metal mesh structures called stents have been developed in order to be able to be deployed in a minimally invasive way. These devices can be brought to these arteries where there is a blockage using a small tube called a catheter through a very small opening in the leg. Before these stents were developed, this procedure was often carried out with just a balloon that was brought with this catheter to the blockage at this remote location in the heart, and the balloon would then be inflated or deployed and compress that blockage against the walls and restore blood flow. This was called balloon angioplasty and was also developed by biomedical engineers. In doing this, the blood would flow and be restored, but was usually only for a limited period of time before the blockage would reoccur. Hence the advancement of stenting technology, whereby now instead of the balloon just being deployed and removed, the balloon was expanded a stent structure also with it, this metal structure you can see here. These stents, you can see the stent here on someone's finger, has struts, as I've said, only a fraction of the size of a human hair. These structures, however, are still strong enough to open up a blocked vessel and keep it open and restore blood flow. There are many different designs of stents for different areas in the body, but here, these stents being used here are coronary stents, and they're placed in the arteries on the surface of the heart. And well over 1 million of these are implanted worldwide each year into these arteries on the surface of the heart, whereas many more are placed in other locations in the body. Coronary stents alone, though, are produced in many cases by companies like Medtronic and Boston Scientific, and about 80% of the coronary stents that are deployed worldwide are produced in Ireland by these companies. Other areas that stents may be implanted are down in the legs, peripheral arteries, femoral arteries in the legs, and up in the neck, in the carotid artery in the neck, in areas like the aorta, the largest artery coming out of the heart, and even in the renal arteries that deliver blood to the kidneys. All of these areas require stents of different designs and different materials. In some cases, these stents can even be what we call self-expanding. They don't need a balloon to expand because they are made from novel materials that actually are super elastic and will expand themselves once pushed out of the catheter. So here we can see one of those self-expanding stents actually opening up as it's released from the catheter. These are the types of materials a biomedical engineer learns about, but also to design and develop the number of different types of designs of stents that get implanted all over the body. You need a lot of other skills too. Skills like computer-aided design, skills like computational modeling skills, so you can virtually test these devices before they get implanted into the body. And of course, significant skills around mechanics, understanding load and strength and stiffness of materials. And of course, the materials that are suitable for going into the body, like biocompatible materials. These are the types of subjects and subject areas that you learn as part of your biomedical engineering program, so that you're in a position to design these type of advanced devices. After graduating from a biomedical engineering program, you have many opportunities for employment. And many of these opportunities are abroad, but there are significant opportunities in Ireland too. The medical device industry in Ireland is extremely strong, with about 450 medical device companies in Ireland alone, and about half of these are actually indigenous to Ireland, where the technologies that underpins these companies has been developed here through startups and biomedical engineers like those that come out of the programme in Trinity. About 30,000 people are employed in the medical device sector in Ireland, and that results in exports of over €12 billion each year. So this is an area of very strong investment, very strong research and development, and a strong area of growth and employment generally in Ireland. Here you can see, for example, that it's not just stents that are produced in Ireland, but about a third of all contact lenses are produced in Ireland. About 75% of the orthopaedic knee production is carried out in companies in Ireland. 50% of the ventilators that are produced to hospitals worldwide are also produced in Ireland. And about 30 million people rely on injectables that are also manufactured in Ireland. Along with, as I've mentioned, about 80% of the coronary stent production is conducted by companies in Ireland also. This shows how strong the employment sector is. But it's not just companies like those that produce these products that employ our graduates. We also have graduates that go to regulatory agencies, that go to consultancy companies, that go into clinical roles such as supporting in hospitals, the equipment and maintaining them, equipment in hospitals, and we have a number that go on to take academic posts. We also have a significant proportion of our graduates continue in further education or postgraduate study, where they continue to carry out research. And many of those stay to carry out research in Trinity College with the leading international academics that we have in our Trinity Centre for Biomedical Engineering. So our biomedical engineering programme, whilst it has research-led teaching by many of these academics, it has a structure that allows the first and second year to be common with all engineering. And this is because all engineers need a good grounding in engineering fundamentals that are common across mechanical, electronic, biomedical, and civil engineering. Biomedical engineering starts to specialise in third year and progressively specialises further in fourth and fifth. You can leave your biomedical engineering programme after 4 years with a bachelor's, or you can stay on for a fifth year to get a master's in biomedical engineering. This decision is made at the end of third year, and if you choose to go on to the fifth year, it opens up the opportunity of doing industrial placement in fourth year or having an exchange with another EU university. Whether you complete after 4 years with a bachelor's or 5 years with a master's, you will carry out a significant research project in your final year. And this is where you will work with the research that is conducted in these internationally renowned labs of the academics that teach on the biomedical program, and work with masters and PhD students in those labs. Biomedical engineering at Trinity is the highest ranked engineering school in the country, according to the Times World University rankings. And the multidisciplinary biomedical engineering that's conducted in Trinity is carried out across multiple schools. And this all comes under the umbrella of our Trinity Centre for Biomedical Engineering, where we have the School of Engineering, School of Medicine, School of Dental Science, and School of Natural Sciences working together to provide solutions to unmet clinical needs. This results in as many as 25 postdoctoral, number of PhD, and a significant number of MSc researchers all working together to, again, provide solutions to unmet clinical needs in biomedical engineering. The world-class research that's conducted in biomedical engineering in Trinity has resulted in considerable amount of research funding to come into the university, and it involves close links with the 5 teaching hospitals in Dublin. All of these enable students to apply the learning and course material that they have to real-life clinical problems by engaging with these clinicians in hospitals and with research labs. Here is an example of some of the state-of-the-art facilities that is available in Trinity to conduct biomedical research. We have the Biomedical Sciences Institute on Pier Street that links with the School of Medicine, the School of Biochemistry and Immunology, for example, And we see here very strong tissue engineering facilities for students to look at developing replacement tissues for the body. Within the Biomedical Sciences Institute, there's also state-of-the-art facilities for anatomy and physiology, which is one of the subjects, as you can imagine, you would learn as part of your biomedical engineering program. And this is because it's so important to understand how the body functions if you need to design devices to interface with it. As part of your program, you will also learn computer-aided design, so you can design products that can address these unmet clinical needs. You conduct this also through biomedical design projects in 3rd and 5th year. You learn about biomaterials and the materials that can be safely implanted in the body without causing any adverse effects. You learn about biomechanics. You learn musculoskeletal biomechanics, how forces can be transferred and regulated within the muscles in the body to move bones within the body, but also you'll understand how forces regulate cells in the mechanobiology area. So how can cells respond to forces? And this also feeds into the area of tissue engineering for developing tissues that can replace the natural tissues of the body. And as I've mentioned, you will conduct a significant research project as part of the biomedical engineering program in your final year. These research projects are conducted with the academics that teach on the program also, and with their research groups. So you will be involved in the cutting edge research that is being conducted within Trinity in the biomedical engineering area. So the staff and the type of research that's conducted by this staff will be overviewed here. So Professor Richard Riley is one of the staff members in the biomedical engineering program. He is a professor in neural engineering. He uses engineering methods to understand brain function, brain trauma, and brain insult. And he designs and creates new devices, neural devices in particular, to look at how to overcome such brain damage. This often involves maybe using electrical signals, like the EEG signals from the brain, to detect this disease and also to help identify that your product can treat it. Professor Kieran Sims carries out research in musculoskeletal and injury biomechanics and also looks at the design of mobility devices, such as wheelchairs, for example. Professor Bruce Murphy has very commercial focused research, where in particular he looks at unmet clinical needs, and an example of a product that he has developed in recent years would be a replacement valve, heart valve, such that when the heart valve doesn't function appropriately in the heart, it can be replaced by an artificial device, again using a minimally invasive approach. Professor David Taylor is an expert in strength and fracture of materials for replacing tissues within the body, such as bone and muscle, and he looks at materials of other animals and plants in order to create tissues that mimic these tissues. It's called biomimetic materials. These materials can be designed taking account of the way that tissues build up their strength and structure in nature and created in a lab to replace damaged tissues. Myself, Professor Tríona Lally, I work on arterial biomechanics and vascular imaging. This is about looking at arteries, testing them, understanding their structure and function, and how disease affects these, and using imaging to identify these changes. I also use computational tools then to design devices that can improve the function of arteries or even overcome disease that has occurred within these vessels, such as stents. Professor David Hoey is an expert in the field of mechanobiology and regenerative medicine and looks at how forces can alter and change cells' response and growth in order to, again, repair damaged or diseased tissues. Professor Michael Monaghan is also looking at this area of cell responses to stimuli, but in particular in the area of heart tissue, and looks at creating tissue in a dish for drug testing also, so tissues can be tested in advance of being placed into the body. Professor Mark Ahern focuses on corneal regeneration and is developing artificial corneas suitable for transplantation to treat corneal blindness. He again uses tissue engineering approaches to create these tissues in a lab rather than having to rely on transplant tissues. Professor Daniel Kelly is a professor in tissue engineering and looks at how adult stem cells, these cells that can be altered and encouraged to turn into many different types of cells, can be stimulated in order to turn into cells that might create cartilage, bone, and ligament tissue. And he uses 3D printing combined with these tissues to create replacement tissues for the body. Professor Conor Buckley also uses tissue engineering approaches to look at how to improve or replace intervertebral discs in order to regenerate and replace these tissues and prevent back pain. This is just an overview of some of the staff that we have in the biomedical engineering area and their research interests, because these are the areas that biomedical engineers work in their research projects and the kind of subjects that are taught on the biomedical engineering program. So you can see from this just the diversity of research and areas within this biomedical engineering program. And if this is something you think that would interest you, and you may have a passion for applying your engineering knowledge, then biomedical engineering program at Trinity College may be one you should consider. Thank you.